Hi everyone, till now we discussed how to calculate the entropy by following a formula which looked like this. We never discussed why we calculate this specific formula for entropy in the first place. In today's video, we will attempt to derive the formula and at the same time try to understand how entropy measures randomness in data. Let's consider a classification problem where the target can take any of the m distinct values. If it is a binary classification problem, it can take either a positive value or a negative value. But for generalization purpose, we considered a multiclass classification problem where m distinct values are possible, but m is finite. We consider a significantly large sample of size n as well. Since we have a sample of size n, we will bifurcate the n values to small chunks of size ni, and ni is the frequency of ith class occurring in the data. In quantifiable terms, we can say that summation of ni is equivalent to n, where I refers to the number of classes. I could be from 1 to m. Now, all these ni's are unknown, and we need to find the maximum probability of occurrence of each of the ni such that it's equally likely for a random sample to take any of the m possible values. This will mean that a randomly drawn sample or a randomly drawn observation from the data shows uncertainty in taking a specific target value. It can take any one of the m values possible. This means that we need to calculate the value of capital P shown over here. Here n is the number of sample, n1, n2, nm are all unknowns, and since we considered the fact that a sample is equally likely to take any of the impossible cases, we have considered the probability to be 1 by m over here. So this is ideally a multinomial distribution, and we will be trying to find the maximum value of p with respect to the unknown values ni's. So we need to find the values which maximizes p. So this is ideally the representation of the problem we are trying to solve. That we have a p over here, we need to find all the ni's which maximizes it. So we will make an attempt to simplify the optimization problem we just defined by not trying to maximize capital P, which is defined over here. We won't be making an attempt to maximize P, but instead we will be making an attempt to maximize a monotonically increasing function of P. We do this all the time. For example, whenever we try to find the maximum likelihood, we always try to find the maxima corresponding to the log likelihood. We will apply a similar sort of adjustment over here, and we will simplify our optimization function further. So the simplified optimization function will involve this to be maximized. So we replaced 1 upon n log, we replaced p with 1 upon n log to the base 2p, which is a monotonically increasing function of p. And we defined p a step before. This is the value of p which we defined previously. We will just apply the property of logarithms. For example, log a into b was decomposed into log a into log b, and then log a upon b was decomposed to log a minus log b, and this is again a logarithm property. And solving a bit further, we get this. C is going to be a constant, even though we can eliminate it while we are calculating the optimization function, but we will allow C to stay as it is over here, and we will eliminate this term further down the calculation. Before we move further, we will define a term called as pi. Pi is equivalent to ni upon n, which is ideally the number of times the ith class is occurring in the sample. Ni is the frequency of occurrence of the ith class, and capital N, this one, this capital N is the sample size which we have over here. Now we will just replace this small ni factorial with capital NPI, which is quite evident from here that we can write small ni as capital N into pi over here. We are just replacing it and we are getting a value in factorial terms in both the sides of the minus sign over here. So now we are going to take advantage of the large sample size which we have taken and then try to find out an approximation of the factorial which is mentioned over here. So when n is very large, we can say that this proposition holds, and we can further simplify both the log base to n in this form. We can write log to the base to n factorial as n log base to n. Similarly, log to the base to npi factorial as a term which will look like this: npi log to the base to npi. So we will solve this a little bit further by again applying the property of logarithms over here, like log a into b is log a plus log b, and eventually we get something like this. So we take these two terms, log base to n and this term, and take log base to n common out of it, we get something like this, and we multiply pi with log to the base to pi, negative sign will come of course, and since we know that summation of pi is equivalent to 1, the summation of pi is equivalent to 1, this entire term becomes 0, so eventually log to the base to n gets cancelled and we get the negative term with summation pi log to the base to pi over here. This is actually the formula for entropy which we have been studying. So this is how the formula of entropy came into place, but still we have an optimization problem to solve. So let's see from where we started with and where we are now currently. So we started with the fact that we need to maximize the value of p. This is the value of p we needed to maximize. We felt that instead of maximizing p, it is quite easy to maximize a monotonically increasing function of p. We went ahead with this monotonically increasing function selected. We did a little bit of calculations and we came to the realization that we have a significantly large sample, then we can definitely use this property. And to all the data structure people, this is actually big O of log n factorial, which is n log n. So this is exactly what we used over here. And once we use such big O notations while we are approximating a function like this constant term is automatically nullified. This term will be so small that we can definitely ignore it. So now we move a step further. This n and n gets cancelled and we get to a point where we are able to reduce our problem that if we have to maximize p, if we have to like maximize p with respect to ni, this is equivalent to solving this complete problem, or it is equivalent to maximizing the entropy. Till now we have defined the value of p, we knew an optimization problem to solve, we were able to convert this optimization problem into this, which is eventually finding out the maximum value of entropy. Now we will take a small numerical example to validate whether this assertion is holding true even for smaller data sets or not. We considered a very small binary classification problem where we considered only two classes like positive and negative or 0 and 1. N0 is the number of observation corresponding to the negative class and N1 is the number of observation corresponding to the positive class. If we consider any record over here, which is like 4 and 2, this is just one example where the number of negative examples are 4 and number of positive examples are equivalent to 2. Now we consider the probability as well, like this is the probability, corresponding probability when we have 6 observations, like the data set is having just 6 observations over here. We calculate the entropy over here. This is the formula for entropy which we used for calculation. This is how we calculated it. We know the value of p as well, which is being calculated over here. in both the cases, this assertion that maximizing the value of P is equivalent to maximizing the value of entropy is faulty. Like the maximum entropy is attained when the positive and negative classes are equal, which is 1, and the same holds for the value of P as well. We can see that the value of entropy and value of P are kind of moving proportionally. Like whenever it's 0.92, it's 0.234 as shown over here. Whenever it was 0.65, it was 0.0094. The same thing happened over here as well. And whenever the value of entropy is 0, the value of P is same 0.016. Now there is one important thing to note over here. Whenever we started our discussion about decision trees, we talked about the type of nodes a decision tree can have. So whenever we are having a situation like this, where only one type of node is present, one type of class is present. For example, in this scenario, we have only 6 observations and all of them are positive. This will mean that we are at a pure node or a leaf node. The entropy in such cases is 0. And let's recall what the definition of entropy actually was. Entropy measures the randomness in the data. When we have a pure node, there is actually no randomness in the data at all. Randomness occurs at points which are similar to this. This is where the randomness is occurring, and the model is unable to decide, or the data point is unable to decide whether it is a positive class or a negative class. In a situation like this, when every class is positive over here, we have a pure node. There is no randomness in the data at all. So I will keep this example over here, which we defined, and we will make an attempt to maximize this objective function. And we have just one constraint over here, which is like summation of all probability should be equivalent to 1. So we kind of get a constraint optimization problem. So we started with the objective of maximizing the value of probabilities, and now we ended up maximizing the entropy with a constraint that all the probabilities should add up to 1. We will apply Lagrange multiplier over here and see what result we get. Let's go step by step through this entire derivation. This is the formula of Lagrange. Like this is one scalar and this is a constraint which we just defined, and this is the value of entropy. We have two unknown variables over here like pi and lambda. We partially differentiate first with respect to pi and then we differentiate with respect to lambda. For extremum points, we equate this differential to 0, and on solving, like once we do a sort of partial differentiation, this and this term gets cancelled out. It's 1 and this is log to the base 2 pi. We get the eventual value of pi to be equivalent to e raised to lambda minus 1. So this is basic calculus I applied over here, and I was able to reduce pi in terms of lambda. Now, what we can do is we will equate L like del L by del lambda to be equivalent to 0, which straight away gives summation pi to be equivalent to 1. And I impute the value of pi over here. And since the summation was from I is equal to 1 till m, and this is actually a constant which is not dependent on I, we get the value of m over here. This still remains the constant. We know that e raised to lambda minus 1 is pi. So we impute pi over here and we get the value of pi equivalent to 1 upon m. And m is actually the number of classes. So in case if it is a binary classification, m will be equivalent to 2. This will imply that pi will be equivalent to 0.5. So this will mean that, and I can go a step further and calculate the Hessian matrix for this as well. But since we have significant results to demonstrate that we have an extremum point, I will not proceed a step further. It's up to you to calculate the double derivative and the Hessian eventually. But as of now, we get the value of pi equivalent to 0.5. And now look carefully what we have derived over here. The highest value of entropy came in our example for a binary classification problem when pi was equivalent to 0.5. So this validates the fact that whenever we need to calculate the maximum value of entropy, uh, both the classes, in case we have a binary classification example, should be equally distributed. This will mean that there is more randomness in the data. Maximum entropy means maximum randomness. Maximum randomness happens when both the classes are equally distributed and an individual observation is unable to decide whether to take a positive class or a negative class. So I think that's it for today, and this explains the entirety of how entropy came into practice. So we can easily say that the entropy, you seeing this column, the value of entropy should be between 0 to 1. So this is the range of entropy. And if we try to plot how an entropy should look like against the value of positive samples, like if it is the positive samples on the x-axis and the value of entropy on the y-axis, we will get a curve something like this, with the lower point being equivalent to 0, the maximum may be occurring at 1. So the value of entropy is equivalent, should lie between 0 and 1. So in our example, we were having a binary classification problem where the number of classes were equivalent to 2. Now let's take a step back and see the problem statement we were trying to solve and the corresponding results which we obtained. So this was a problem statement which we were having, like we were considering a classification problem, which is a multi-class classification problem having m distinct values. We had a data set of size n, where n is significantly large, under the assumption that a drawn sample or a drawn observation can take each of the m possible values, which will mean that any randomly drawn sample can take any of the m possible values which were there in the target. We needed to find the maximum probability of occurrence of each of the ni's. In other words, we needed to find this. So this was the optimization problem, which we eventually decomposed the actual optimization problem into, and this was the constraint. On solving it, we were able to get the probability of I, where Pi was equivalent to Ni upon N, as described previously, as equivalent to 1 upon M. Now we need to find out what is exactly the maximum entropy possible. Like we needed to maximize this specific function. Now, since we obtained the exact value of Pi, we need to find out what is the maximum entropy or the maximum value of the function which we can obtain over here. For doing so, we just plug the value of Pi equivalent to 1 upon m in this formula. And this is the maximum entropy which we are getting, the maximum value of this function which is highlighted. So I plug in the value of Pi as equivalent to 1 upon m. So it becomes 1 upon m log to the base to 1 upon m. 1 upon m comes out because this is a constant term, and since the remaining term log to the base to 1 upon m is not having any dependency on I, it is actually a constant. So the summation resolves to m times log to the base 2m, and on solving further and cancelling the terms, we can see that the maximum value of entropy comes out to be this, which is obtained when I cancel out m, and log to the base to 1 upon m could be written as minus of log to the base to m, because this is an inverse, and both the minus sign gets cancelled and eventually we get a positive log to the base to m. Now, this is the upper limit of entropy, and the lower limit of entropy, as we discussed previously, is going to be 0, because the entropy of 0 is obtained when we have a leaf node or a pure node. And in case we have a leaf node, then all the observations belong to the same class and there is no randomness at all. So mathematically, we can write the value of entropy as 0 less than equal to the value of entropy should lie between 0 to log base to m. Now if m was 2, like in case we had a binary classification problem, the log to the base to m converts to 1. That's why we were having the range of entropy between 0 to 1, and that holds only for a binary classification problem. That won't be possible for any other classes. So if we have the value of m greater than 2, like 3, 4, 5, we will have the different value of upper bound and not 1. So this table shows the entropy values corresponding to the classes which are more than 2. So the entropy value corresponding to 3 over here is 1.5, which is definitely greater than 1. Corresponding to 4 is 2, corresponding to 8 is 3, and so on. So the entropy, maximum value of entropy keeps on increasing if in increase in number of classes. This means that the randomness increases with the increase in classes. This is one of the possible reasons why the performance of decision tree suffers when we have more and more classes. And that concludes the video. And in this video, we discussed how the formula corresponding to entropy was derived, how entropy could be maximized, and in what range entropy lies. So thanks for watching this video. See you in next class.